This is my fourth video lesson on Unit 5C. In this lesson, we'll be talking about how do intramolecular forces affect properties of molecules, such as phase and boiling point. Let's go to page 16 in the class packet. Motivation. Which state of matter, solid, liquid, or gas, will have the highest intramolecular forces, and why? So take a moment to analyze this diagram. Learning target. At the end of the lesson, I'll be able to compare intramolecular forces in the states of matter and explain how intramolecular forces affect boiling point of an atom or molecule. Homework will be number 4, which is a unit pod based off this lesson. If you recall from Unit 1, you should know that solid has the strongest attractive forces, then liquid, then gas. So why is that? If you look at the diagram, in the solid state, the atoms are much closer together than the liquid and the gas. So trick understanding number 1, what is the relationship between intramolecular forces and distance? The closer the atoms, the stronger the intramolecular force. Learning check number 1, which statement explains why Br2 is a liquid at STP and I2 is a solid at STP? Pause this video and resume once you complete it. Since I2 is a solid and Br2 is a liquid, I2 must have stronger intramolecular forces than Br2. So the answer is choice 4. At STP, iodine, bromine, and chlorine are diatomic molecules. Iodine is a solid, bromine is a liquid, and chlorine is a gas. So the molecules of iodine have stronger intramolecular forces than bromine, and the molecules of bromine have stronger intramolecular forces than chlorine. So why is that? So this has to do with the size of the molecule. We will discuss later how the size of the molecule affects the strength of the intramolecular forces. Let's organize the following phase changes as either endodermic or exodermic. Keep in mind, endodermic means absorbing energy, exodermic means releasing energy. Melting is a process from solid to liquid, so in order to go from solid to liquid, you need to absorb energy, so it's an endodermic process. Another way to think about it is that the atoms in the solid state are slower than atoms in the liquid state. So when they undergo melting, the atoms in the solid state absorb energy to move faster. Freezing is the opposite of melting, therefore is an exodermic process. So energy is released during freezing. So how does that work? Atoms in the liquid state move faster than atoms in the solid state. So when it undergoes freezing, the atoms in the liquid state lose energy to the surrounding area and move slower as a result. Boiling is going from liquid to gas. It is an endodermic process. Why is boiling endodermic? Because atoms in the liquid state are slower than atoms in the gas state. So it must have absorbed energy when it went from liquid to gas. Condensation is the opposite of boiling. Therefore, it is exodermic. Why is condensation an exodermic process? It's the same reasoning as freezing. Atoms in the gas state are much faster than atoms in the liquid state. So when it went from gas to liquid, it must have lost energy to the surrounding environment. So the atoms move slower as a result. Sublimation is going from solid to gas. Since the atoms move much faster when they go from solid to gas, it must have absorbed energy. Deposition is the opposite of sublimation, so it's an exodermic process. Now we're going to explain the following in the context of intramolecular forces rather than the speed of atoms. We know melting is an endodermic process and energy is being absorbed. But what is the energy doing besides speeding up the atoms? If you recall, solid have stronger intramolecular forces than liquid. Remember, think of intramolecular forces as attraction, like little magnets. So to go from solid to liquid, you must break those intramolecular forces. So the energy that's being absorbed is being used to break the intramolecular forces between the atoms. So remember, BARF, breaking absorb releases forms. So energy is being absorbed to break the intramolecular forces in the atoms in the solid state so that the atoms can move further apart in the liquid state. Freezing is the opposite of melting and is an exodermic process. Why is that? If you look at the particle diagram, atoms in the liquid state have less intramolecular forces than atoms in the solid state. So to go from liquid to solid, you must have formed new intramolecular forces. So remember, BARF, breaking absorb releases forms. Since you're forming new attractions, energy must be released. Boiling is an endothermic process. Why is that? It's a similar reasoning to melting. If you look at the particle diagram, atoms in the liquid state have more intramolecular forces than atoms in the gas state. Therefore, you must have used the energy to break the intramolecular forces to go from liquid to gas. Condensation is the opposite of boiling and is an exothermic process. Why is that? If you look at the particle diagram, the intramolecular forces of the gas is less than that of the liquid. So when it goes from gas to liquid, you must have formed new intramolecular forces, and forming new attractions releases energy. Remember, BARF, breaking exort releases forms. So that's why condensation is an exothermic process. Learning check number 2. Which process is exothermic? Pause the video and resume once completed. So the answer is choice 3, condensation of ethanol vapor. Condensation is an exothermic process. Learning check number 3. Which phase change is exothermic? Pause the video and resume once completed. So which process releases energy? That would be choice 2. Why? Because water in the liquid state moves faster than water in the solid state. So energy must have been lost or released into the environment. That's why it's exothermic. Let's use this diagram to analyze the relationship between the strength of intramolecular forces and the distance. The x-axis represents the distance between the two atoms. The y-axis represents the forces or interactions, whether there's attraction or repulsion. So if we look at the diagram, why is there repulsion if the atoms get too close? If atoms get too close, the electron clouds of both atoms will overlap. Remember, opposites attract, same charge repel. So the repulsion is coming from the electron clouds of both atoms. What happens to the force of attraction as the distance between the atoms increases? So notice as the atoms move further and further away, the forces of attraction decreases. One way to think about this is think of two magnets. If the two magnets are very far apart, they will not be attracted to each other. Now we're going to talk about how intramolecular forces affect the boiling point. We are going to use this graph in order to determine the relationship between intramolecular forces and boiling point. There are two trends, A and B. We will analyze both of them. The y-axis is the boiling point, and the x-axis is the molecular mass. The first question, state the prevalent intramolecular force of H2O, H2S, H2SE, and H2TE. O, S, Se, and Te are in the same group, group 16, so we expect these molecules to have the same shape, which is bend. H2O have an H and an O, therefore the prevalent intramolecular force is hydrogen bonding. H2S is a polar molecule because it's a bent shape. Remember, SNAP, symmetrical nonpolar, asymmetrical polar. Since it's asymmetrical, it is polar. Since H2SE and H2TE have the same shape as H2S, they are polar and they have dipole-dipole interactions. Question 2. Identify trend A. Substances with blank intramolecular forces have blank boiling point. Notice that water have a higher boiling point than the other three substances. If you look at the intramolecular forces, water has a stronger intramolecular force. It has hydrogen bonding. We know hydrogen bonding is stronger than dipole-dipole. So substances with a stronger intramolecular force have a higher boiling point. That's the relationship. Question 3. State the intramolecular force in trend B. If you look at trend B, you have atoms from group 14 bonding with hydrogen. So they will have the same shape. So what's the intramolecular force present in those substances in trend B? They all have van der Waals dispersion forces. Unlike trend A, in which one substance had a stronger intramolecular force, in trend B, they all have the same. So the type of intramolecular force is a constant variable here. Question 4. Identify trend B. Notice there's an upward trend. There's a direct relationship between boiling point and mass. So substances that are bigger have higher boiling point. Question 5. Is trend B observation also true for trend A? Yes, but only if they have the same intramolecular force. Notice that H2S, H2SE, and H2TE have the same intramolecular force. Dipole-dipole, Both trends have the same relationship between boiling point and mass. The only exception is water, because water have a different, stronger intramolecular force. Check of understanding number 3. What is the relationship between intramolecular forces and boiling point? So they have a direct relationship. As the intramolecular forces become stronger, the boiling point increases. Why is that? Boiling, as you know, is an endodermic process. So the stronger the intramolecular force, more energy is required to break those intramolecular forces. Just to review, this is showing the relative strength of each intramolecular force. Molecule ion is the strongest, while dispersion is the weakest. There is a direct relationship between intramolecular force strength and boiling point. The stronger the intramolecular force, the higher the boiling point. Learning check number 4. Which statement explains why H2O has a higher boiling point than N2? Pause the video and resume once you complete it. So since water has a higher boiling point, it has stronger intramolecular forces. Water has hydrogen bonding. N2 only has van der Waals dispersion force. Learning check number 5. Which substance in the table below has the strongest intramolecular force? Pause the video and resume once you complete it. So we have to look at the boiling point. So since HF has the highest boiling point, it has the strongest intramolecular force. We are going to look at another graph to figure out the relationship between size of a molecule and intramolecular force. On the y-axis is the boiling point. On the x-axis is the number of carbons. So these are hydrocarbons. Here's the structural formula of each of these hydrocarbons. So from methane to octane, it gets bigger. Question 1. State the intramolecular forces in hydrocarbons. If you look at all these hydrocarbons, there's only one intramolecular force, which is the van der Waals dispersion force. What's the relationship between intramolecular force and size of a molecule? So from methane to octane, it gets bigger and the boiling point increases. We know the relationship between boiling point and intramolecular forces is a direct relationship. So as intramolecular forces increases, boiling point will also increase. So the relationship between intramolecular forces and size of molecule is that as the molecules get bigger, the intramolecular forces increases. Why is that? Dispersion forces are caused by the attraction of electrons and nuclei between atoms and molecules. Larger molecules have more electrons and nuclei to form more dispersion forces. Larger atoms have bigger electron clouds to form more dispersion forces. In addition, the larger the atom or molecule, the more surface area there is, so there's more opportunities to form those intramolecular forces. Learning check number 6. The strongest van der Waals forces of attraction exist between molecules of what? Pause the video and resume once completed. So the strongest intramolecular force will be iodine because it's the biggest out of all 4. So that's why iodine is a solid, Br is a liquid, and Cl2 and fluorine are gases. Iodine is the biggest, therefore it has more and stronger intramolecular forces. That's why it exists as a solid at STP. So in summary, the strength of intramolecular forces depend on the type of intramolecular force and the size of the molecules. So remember, structure influences property. So the structure, which is the type of intramolecular force, and the size of the molecule influences properties such as boiling point and phase. So now we're going to analyze the boiling point and melting point trend on the periodic table. We are going to analyze the trend for metals and nonmetals. So we're going to look at group 1 and group 18. Boiling and melting involve breaking the forces of attraction between molecules and atoms. So we expect the boiling point and the melting point trend to be the same. So we're just going to do the boiling point trend. We're going to start with the metals trend. So first, go to table S in your reference table. Look up the boiling point of each metal element in group 1. So here are the boiling points. So what's the trend here? It is increasing up the group. So what is the force of attraction that's present between metal atoms? It is the metallic bonds. So from Li to Cs, does the strength of the metallic bond increase or decrease down the group? So we know the higher the boiling point means a stronger force of attraction. So the strength of the metallic bond will decrease down the group because the boiling point decreases as you go down. Why is that? If you recall from Unit 4, which was the periodic table trend, there were two main variables, effective nuclear charge and shielding. Since effective nuclear charge is constant, the shielding effect is going to be the dominating factor. As we go down the group, there is more shielding. There is more inner electrons. Since there's more inner electrons, there is more competition for the attraction of the nucleus. Therefore, it's harder to attract an electron in a metallic bond. That's why metallic bonding gets weaker as you go down the group. As you go down the group, metallic bonds are weaker for larger atoms, because as atoms increase in size, the distance between the nuclei and the mobile sea of delocalized electrons increases. Effective nuclear charge is constant. Now we're going to talk about the nonmetal trend, so let's look at group 18. So take a moment to use table S and look up the boiling points of each element in group 18. So here are the boiling points for group 18. So it increases as you go down the group. So it's the opposite of metals. So what force of attraction is present in non-metal atoms? So that's the van der Waals dispersion force. From helium to radon, does the strength of intramolecular force increases or decreases down the group? Since the boiling point increases, the strength of intramolecular forces must also increase. The nonmetals trend should be easier to see. As you go down the group, the atoms get bigger. As atoms get bigger, there's more surface area, there's more intramolecular forces. If there's more intramolecular forces, there's a higher boiling point. As you go down the group, the intramolecular forces are stronger for larger atoms because as atoms increase in size, there are more surface areas, therefore there's more intramolecular force. If there's more intramolecular force, the higher the boiling and melting points. So this concludes the video lesson for today. Remember to do the Junipod homework.